Okay, so today we move to chapter 5, which is on set theory. And we've actually covered a little bit of the material in section 5 already, right? So recall that if U is some universal set and A and B are subsets of U, so we have two sets A and B, then we defined a bunch of things already. So we defined what it meant to be this new set, the union of A and B, the intersection of A and B, the set theoretic difference of A and B, and also the complement of A. So we already defined these four set operations. And we talked about how sometimes the universal set is sort of understood by everybody. And so you might not mention it explicitly in other classes. So for example, in calculus, a lot of times the universal set was the real numbers. So it was sort of understood that everybody was talking about the universal set was the real numbers. So like, for example, the complement, right? This was defined to be everything that's not in A. But in order to know what that set is, everything that's not in A, you need to know what everything is, right? This is all the elements of the universal set that are not in A. So even though in previous classes you maybe weren't too worried about a universal set because there was sort of an implied inherent one, when we deal with set theory, we'll basically always say, let U be a universal set, and then we'll do the problem. Okay. Okay, so let me make the first new definition in this section. So now we're going to really dig into to chapter 5. So if A is any subset of a universal set U, then I'm going to define the power set of A, and it's denoted with the script P of A, so P for power set, is the set of all subsets of A. It's the set of all subsets of A. So another way to say this is that the power set of A is the set of all sets that are subsets of A. All subsets of the universal set that are subsets of A. Okay, and for those of you following along at home with LaTeX, the way to get this sort of script P is to do \math cal brackets P. That's for math calligraphic font. Okay, so that's the definition. But anytime you see a definition, you should think, okay, well, what does that actually mean? So by that, we should do an example, right? So let's let A be the set, say two elements, A and B, right? Then the power set of A is defined to be all of the subsets of this set. Well, how many subsets does A have? Well, we said that the empty set is always a subset of A, no matter what A is. So and it's the only subset that has 0 elements in it. Also, just the set containing A, that's a subset of A. Also, just the set containing B, that's a subset of A. And also, the whole set itself is a subset of A. But that is every single possible subset of A. So here, the power set of A contains 4 elements: the empty set, the set containing A, the set containing B, and A itself. Okay, again, notice here that I didn't really specify the universal set in this example, because actually the universal set doesn't really matter when it comes to defining the power set, right? Whether the universal set, no matter what the universal set was here, the power set of A would have been the same thing. Also note that, right, the power set consists of all possible subsets of A. So one thing that's always going to be in the power set is the empty set. So empty set is always in the power set of a set, no matter what the set is. Let's say power set of X. And also the set itself is always a subset. So X is always in, no matter what set X is. So the power set always at least contains two elements, unless X is itself the empty set, I guess. But the power set always contains the empty set and the whole set itself. Right, so you could say the empty set and A are elements of the power set of A, and that will be true for every set A. Okay, another example. If B now is A, B, C, a 3-element set, well, what's the power set of B? The power set of B is the set of all subsets of B, right? So there's a single 0-element subset. There's 3 1-element subsets of B, the set containing A, the set containing B, the set containing C. There's also 3 2-element subsets of B, right? The set containing A and B, the set containing A and C, and the set containing B and C. And then there's a single 3-element subset of B, namely B itself. And so pretend I wrote that all in one line. And so this power set has 8 elements. One way to think about this is that B is just A union the set containing C, right? B is just A plus an element. So the power set of B should contain the power set of A as a subset, all right? Because every subset of A is also a subset of B, because A is a subset of B. So like here, I can find the power set of A sitting here. And then the other 4 elements is just like I added C to every element of the power set of A. Right? So every element in the power set of B either contains C or doesn't contain C. If it doesn't contain C, it's just something from the power set of A. If it does contain C, then it's just like you added C to the empty set, you added C to the set containing A, you added C to the set containing B, and you added C to the set containing A and B. So there are 8 elements here. Okay, but this was just an illustrative example. We'll learn more about the power set. We'll prove some things, and we will, I'll give you some homework exercises. This is a sort of a fundamental set associated to any set. Okay, recall also that we defined the cardinality of a set. So the cardinality of a finite set is just the number of elements in the set. Okay, so if you have an infinite set, you just say it has infinite cardinality. But if you have a finite set, the cardinality is just the number of elements. Okay, so we denote the cardinality of a finite set A by either card of A for cardinality, or we can use the absolute value bars, but you would still pronounce that the cardinality of A. Okay, and there is also a way to talk about the cardinality of infinite sets. And in fact, there are different sizes of infinity. This is one of the really important mathematical breakthroughs of the 1800s, Georg Cantor, the father of modern set theory. But it will take a few weeks before we can talk about different cardinalities of infinity. We'll do this, I think, in week 9 or week 10. It's pretty fun, but for now, we need to understand finite sets first. Okay, so I'll use both notations sort of interchangeably, but for now, let's stick with this card notation. So if you go back to the previous page, cardinality of A is a 2-element set. So the cardinality of A is 2. It's a finite set. It has 2 elements in it. The cardinality of B, which was the set ABC, it has 3 elements in it. So B has cardinality 3, you would say. The cardinality of the power set of A. The power set of A had 4 elements in it, right? So the cardinality was 4. The cardinality of the power set of B. Let's see, there's 4 blue elements and 4 green elements. So at cardinality 8. Okay, quick question. What's the cardinality of the empty set? Well, the empty set's certainly not an infinite set, so it must be a finite set. How many elements are in the empty set? There are no elements in the empty set, so it has cardinality 0. But the cardinality of the power set of the empty set. Now, what's the power set of the empty set? The power set of the empty set is the set of all subsets of the empty set. This is all subsets of the empty set. Now, the empty set contains no elements, but it does have a single subset. The empty set is a subset of itself. So the power set of the empty set is a set containing the empty set, because the empty set is a subset. Put it this way, the empty set is a subset of the empty set, so it's in the power set. So the cardinality of the power set of the empty set is actually 1. Now, why did I include this? Because I want to ask you the following question. Let's suppose that A is a set with cardinality n. What is the cardinality of its power set? Okay, so hopefully, let's see. Hopefully you can see this pattern. If n is 0, the power set of the empty set, if n is 0, then the cardinality of the power set is 1. If n had size 2, the cardinality of the power set was 4. If it had size 3, the cardinality was 8. So it seems like we have a guess here of 2 to the n. It's at least consistent with the data we have so far, right? And you should prove this as an exercise, but I'll call it a theorem here. If cardinality of A is n, then cardinality of the power set of A is 2 to the n. Okay, so you should prove this because it's a nice exercise in proof by induction. What do? Well, the base case is when n equals 0. When n equals 0, the only set with 0 elements is the empty set. And we already saw that the cardinality of the empty set is 1. Sorry, the cardinality of the power set of the empty set is 1. So that'll be the base case. For the induction step, what you do is you assume that any set with cardinality k has a power set with cardinality 2 to the k. Now you consider any set of size k plus 1. But now you go back to this logic that I sort of hinted at when we're considering A and B, right? So it's like you have a set of size k. That's like what's happening here. We know that every set of size k has a power set of cardinality 2 to the k. And then we consider a set of size k plus 1. And the point is that every subset of that set either contains the k plus first element or it doesn't contain the k plus first element, right? Now, how many subsets of B of this set of size k plus 1 do not contain the k plus first element? Well, that's just all the subsets of the first k elements. So by the induction hypothesis, there will be 2 to the k subsets of B that don't contain the k plus first element. How many subsets do contain the k plus first element? Well, again, if you contain the k plus first element, then you just look at all the rest of the elements that are in that subset. There'll be one for every element of the power set of the first k. Right? It's like you'll have all the ones that don't contain C here. That's just like the power set of A and B. And all the ones that do contain C, you can also think of as just being like the power set of A, except you also threw in C. So there's 2 to the k of the ones that don't contain the last element. There's 2 to the k of the ones that do contain the last element. And so total, there's 2 to the k plus 2 to the k, which is 2 to the k plus 1. Okay, so I included a proof sketch in the typewritten notes, but you should write it up carefully in your notes. I'll just say by induction. I get to do that because I'm the one lecturing. Right? Okay, so that's a lot of the definitions that we'll need in this chapter. We won't actually have all that many new definitions, at least for now. So the next section is really about how do you prove things about sets. This is really what 5.2 is about. Okay, so let me just recall a definition that we covered already. We said that we define what it meant to say that A is a subset of B. What did this mean? To say that A was a subset of B meant if X is in A, then X is in B. That's the definition of that symbol. Maybe I should quantify and say for every X in the universal set, if X is in A, then X is in B. That's what it means to say that A is a subset of B. And really, this is how you prove that something is a subset of another thing. It's also tells you how to prove that something is not a subset of another thing. So let's just list this as a technique, and then I'll give you some examples to show what I mean. So this is called element chasing. Kind of a nice name. So to prove that A is a subset of B, what you do is you suppose that X is in A, and you suppose that it's an arbitrary element. What do I mean by this? I'll tell you, I'll show you specifically in a second. But by this, I mean, you choose an X in A, but it has to be able to be any element of A. In other words, you don't use anything special about the element X, except that it is an A. So you choose an arbitrary element of A. All you know about this element is that it's in A. You don't know anything else about it. But then you show that X is in B. So in other words, you take an element and then you chase around and then you try to find it in the set that you want it in. Okay, again, this means that you don't get to assume anything about X, except that it is an A. Okay, if you want to disprove that A is a subset of B, how can you disprove that A is a subset of B? Well, to disprove it means that you would show that this conditional is false. How can you show that this conditional is false? It'll be false if the hypothesis is true and the conclusion is false. Which means that to disprove that A is a subset of B, you just need to find some X in A such that X is not in B. that would disprove, I mean, that would show that that conditional is false, right? So to show that one set is a subset of the other, you need to give a proof. To show that one set is not a subset of the other, it suffices to give an example generally. Okay, because, right, really the picture of being a subset, right, looks like this. This is what it means to say that A is a subset of B. And to prove that to disprove this picture, what you need to do is you need to show that there's actually something here. And what is that? That's a thing that's in A, but not in B. That's how you would show that A is not a subset of B. Okay, so let me give you some examples, sorry, at least one example, of a proof and a non-proof where I really want to emphasize that when you do an element chase, you need to be careful about taking an arbitrary element of A. So let me show you. Here's a nice theorem. So let's let A be the set of all multiples of 4. And let's let B be the subset of even integers. And I suppose here, like, my universal set is probably the integers. So those are both subsets of my universal set. Then one of these is a subset of the other. Hopefully you can see that A will be a subset of B. The multiples of 4, that's a subset of even integers. Some multiples of 4, some even integers are multiples of 4, some are not, but every multiple of 4 is even. Okay, so let me first give you a non-proof of this fact. Okay, so remember, the way to prove this is to take some x in A, suppose x is in A, and show that x is in B. So here's my non-proof. So since 4 is equal to 4 times 1, therefore 4 is an A. Right? That's true. Now observe that 4 equals 2 times 2. So 4 is even. Hence 4 is in B, because B is the set of all even integers. Therefore, A is a subset of B, because I've taken an element of A and shown that it's in B. Okay, this is not a proof that A is a subset of B. All it proves is that 4 is in A and 4 is in B. This is not a correct element chasing proof because I didn't pick an arbitrary element of A. I picked a specific one. I specifically picked 4, and then I used the fact that it was 4 to prove that A was in B. I need to pick an arbitrary element of A, and I can't use any property about it other than it is a multiple of 4. So what's the correct proof? The correct proof is suppose x is an A. Here I'm taking an arbitrary element of A. Now, since x is a multiple of 4, that's what it means to be an A. This means there exists an integer k such that x is equal to 4 times k. Right? But then x, which is 4 times k, is 2 times 2k. And by the closure of the integers, 2k is an integer. All right, k is an integer. Therefore, 2k is an integer. And now x is 2 times an integer. So by the definition of evenness, x is even. So x is in B. We conclude that A is a subset of B. Okay, so again, the technique here is element chasing. How do you prove that A is a subset of B? You pick an arbitrary element of A and you show that it's in B. And by picking an arbitrary element of A, what I mean is you pick an element and you of A, but you only use the fact that it's an A. You use nothing else special about that element. So here, all I use is that X is an A. I wrote it as 4 times K, and then I showed that it satisfied the property of being in B. Okay, and you will use element chasing proofs for the rest of your mathematical career, probably beyond that. This is just the standard way of showing that something is a subset of another set. Okay, let me give you another example, another proof. Okay, so suppose that A, B, and C are sets, subsets of some universal set. Okay, then I claim that A minus B union C is a subset of A minus B union A minus C. Okay, I will prove this for you. And the proof is just an element chase. So how do you do an element chase? You suppose you have an element of the left-hand side and you show that it's in the right-hand side. So suppose that X is an A minus B union C. Now, by definition, this means that X is an A, and X is not in B union C. That's what it means to be an A minus B union C. Well, to say that X is not in B union C means that X is not in B and X is not in C, right? Because, right, this is just an aside. B union C, this is the set of all elements such that X is in B or X is in C. So if you're not in that, it means that you satisfy the negation of this. And the negation of that X is in B or X is in C by De Morgan's law is X is not in B and X is not in C. Right? So therefore, X is not in B and X is not in C. Okay, now we know that this element X is an A and it's not in B. Since X is an A and X is not in B, therefore, X is in A minus B. That's the definition of being in A minus B. And now if it's in A minus B, it's definitely in this union because this union contains A minus B. So X is in this union because this union is only bigger. So what I do, I started with an element of the left-hand side and I showed it was in the right-hand side. Therefore, A minus B union C is a subset of A minus B union A minus C. Okay, so this is a nice standard element chasing proof. And I think that, like, you know, the statement of this is, it's not that easy to see whether it's true or not. In fact, let me ask you a question. What about the reverse inclusion? So we just showed that the right-hand side is, sorry, the left-hand side is a subset of the right-hand side. So my question is the right-hand side, rather, a subset of the left-hand side? Now, how could you go about trying to understand this thing? To me, it would seem like we should try to draw the Venn diagrams of these two sets and see if we think they're equal, or if one is a subset of the other, rather. If it seems like one is a subset of the other, then we should try to go ahead and prove it using an element chase. If it seems like that's not always the case, then we should try to cook up a counterexample. So let's think about this picture. So the general Venn diagram for 3 sets looks like this. Right, this is A, B, C, A, B, C. So what is this left-hand side? A minus B union A minus C. So A minus B is this bit. It's like everything in A that's not in B. A minus C is this bit. And if you union them together, you get everything that's in green here, right? So the green color here is the left-hand side set. What about the right-hand side? The right-hand side is A minus B union C. So B union C is everything that's in B or in C. And if I subtract that off from A, I get this. So in fact, it seems like these two sets in general will not be the same. Right? So does this prove that they're not the same? It highly suggests that they're not the same, but a Venn diagram is not the same thing as a proof, right? How do you, sorry, not the same, I should say not a subset of, right? It certainly looks like the blues thing is a subset of the green thing, but the green thing is not a subset of the blue thing. But this Venn diagram isn't a proof, it's just intuition. To prove that it's not a subset, what I need to do is I need to give an example of some sets, A, B, and C, and give something that's in the left-hand side that's not in the right-hand side. That's how you disprove that something is a subset of the other. So what I need is I'm going to need to find a set where there's actually something in one of these extra green portions. So what I want is some A, B, C such that there is something that's, say, in this part, in A intersect B minus C. If there's something in that part, then the green thing will be bigger than the blue thing because the green thing will contain it a bit more. So let's just cook up a counterexample. So let's let A be the set 1, 2. Let's let B be the set 1, 3. Right, so now A and B are intersecting. They intersect in 1. So it's like the black part will contain 1. So if I just make sure that that thing is not in C, I'll get a nice counterexample to this. So let's let C be the set, I don't know, 2, 3. Okay. Am I too low on this page? Maybe not yet. Okay, then A minus B here is just the set 2. A minus C is just the set 1. So the green thing is the union of these two things, which is the set 1, 2. But B union C is 1, 2, 3, which means that A minus B union C is the empty set. So in this particular example, 1 is in the left-hand side, but it's not in the right-hand side. So this gives an explicit counterexample that shows that in general, the green thing is not a subset of the blue thing. Right? So certainly 1, 2 is not a subset of the empty set because the only subset of the empty set is the empty set itself. Okay, so that's how you show that two sets are, that one set is a subset of the other set, of another set. Let me tell you how to prove that two sets are equal. So to prove that two sets, A and B, are equal, how do you prove that two sets are equal? The technique here is prove that A is a subset of B and B is a subset of A. This is generally how you prove that two sets are equal. Because if you could prove these two things, then A and B would have to contain exactly the same elements, right? Every element of A would be an element of B, and every element of B would be an element of A. So therefore, they must contain exactly the same elements. And this is, again, a technique that you will use over and over and over and over again in your future math classes. They say, show these two sets are equal. You show that they're subsets of one another. This is like the standard technique. So let me illustrate that. So let's let A, B, and C be sets. Then I claim that if you take A and you subtract off the union of B and C, this is actually equal to the intersection of A minus B and A minus C. So whenever you see someone telling you to prove that two sets are equal, the first thing to do is to think, oh, well, I know how to do this. I'll just show that they're subsets of one another. How do I show that they're subsets of one another? I'll do an element chase in both directions. So let me just tell my reader what I'm doing. We will prove both inclusions. So I'm telling my reader, in order to prove that these two sets are equal, I'm going to do the technique that I wrote in red here. I'm going to show that the left-hand side is a subset of the right-hand side, and I will show that the right-hand side is a subset of the left-hand side. Okay, then I'll give my reader a little bit of direction. This is just like it's like a paragraph number or a section number or a case number. I'll include this little subset symbol to say, I'm doing this direction currently. All right, and then later on, I'll do the other direction. I'll do this. And so if my reader is looking at this proof, they know exactly where to look and what I'm doing at every point. Okay, so how do I prove the first inclusion? I do an element chase. Suppose that X is in A minus B union C. Okay, then, by definition of this minus symbol, X is in A, and X is not in the union of B and C. But we already discussed that since X is not in the union of B and C, X is not in B and X is not in C. Right, so now I picked an arbitrary element of A minus B union C, and I've discovered that this element is in A, it's not in B, and it's not in C. Okay. Now, since X is in A and X is not in B, we have that X is in A minus B. Similarly, since X is in A and X is not in C, X is in A minus C. Finally, since X is in A minus B and X is in A minus C, by definition, it's in the intersection. X is in A minus B, intersect A minus C. So this shows that the left-hand side is a subset of the right-hand side because the element chase worked. Now we do the opposite inclusion. Suppose that X is in the right-hand side. Then by definition, X is in A minus B, and X is in A minus C, because it's in the intersection of those two sets. Right, since X is in A minus B, this means X is in A and X is not in B. Similarly, since X is in A minus C, X is in A and X is not in C. So what do I know about X? I know that X is in A, X is not in B, and X is not in C. Okay. right? Now, I'm having one note problems again. Jeez, this always happens. Okay, let me try to close one note and then, oh no. Sorry about this. I'm having one note problems. If I close this window, what happens to the Zoom share? How often does this happen in your other classes? That's my question. Let's close OneNote. Let's open OneNote. And let's share again. Okay, my apologies. So right now we have that X is in A and X is not in B, and X is in A and X is not in C. But now, since X is not in B and X is not in C, we have that X is not in the union. Now I have X in A, X not in the union. Therefore, X is in A minus the union. So this shows that the right-hand side is the subset of the left-hand side. And now, since we've shown both inclusions, that shows equality. So since we have shown both containments, this proves equality. Okay, so these set theoretic proofs are frankly a little bit dry. It's just like basically writing down the definitions of what all these sets are. But this technique, again, is completely ubiquitous in mathematics. For the rest of your life, whenever you want to show that two sets are equal, your first thought will be, I'll show both inclusions. And if that's what happens, then I have done my job, at least for this particular part. Okay, last definition for today, which actually is maybe something we've defined already. But maybe we didn't write it in the form of a definition. Let A and B be sets. Then I say that A and B are disjoint if the intersection of A and B is the empty set. Okay, so disjoint sets have nothing in common. Disjoint sets have nothing in common. So here's the theorem. Let A and B be sets. If A is a subset of B, then A and B complement are disjoint. Okay, this seems reasonable enough, right? Why? If A is a subset of B, it means that the picture looks like this, right? And they're staying inside some universal set. And if the picture looks like this, then B complement is this blue part, and A is this green part. And so if this picture looks like this, then it certainly seems like A and B complement must be disjoint. Another way to say that A and B complement are disjoint, right, is A intersect B complement equals the empty set. But the question becomes, how do we prove that something is equal to the empty set? Well, I said that you can prove that to prove that two sets are equal, you prove that each set is a subset of the other. So certainly the empty set is a subset of every set. But how do you show that something is a subset of the empty set? How do I show that if X is an A intersect B complement, then it's in the empty set? That seems like a hard thing to do. But the thing to realize here is that the negation of a set being empty is that it contains an element, which is like a really nice concrete thing to work with. So it seems like if you're trying to show that something is equal to the empty set, you could either do contrapositive or proof by contradiction, depending on the situation. Because if you negate the second half of the statement, that A intersect B complement equals the empty set, you get that you negate it means that there's an element in A intersect B complement, and then you can try to show that the first part is false. So this technique here, it's like a meta technique. So to prove a set is empty, try contrapositive or perhaps contradiction. Maybe I shouldn't call this a technique because it's not really a technique. Let's call this a pro tip. So let's prove this. So it suffices to prove the contrapositive because I'm trying to prove an if then. In order to prove if P then Q, you can prove if not P, Q then not P. So suppose A and B complement are not disjoint. Then there exists some element X that's in the intersection. That's what it means to say that A and B complement are not disjoint. But for this element X, it's in the intersection, so X is in A and X is in B complement. In other words, X is in A and X is not in B. But if you have an element that's in A, but it's not in B, that's exactly how you prove that A is not a subset of B. It fails the definition of A being a subset of B. Therefore, A is not a subset of B. And so we've proven the contrapositive of the statement, which means that the original statement is true. Okay, so today we covered the definition of the power set of a set. You'll have some problems on that. Definition of cardinality. Then we discussed sort of three of the very, very, very basic techniques of proving things about sets. In order to prove that one set is a subset of the other, you do an element chase. In order to prove that two sets are equal, you show that they're subsets of each other. And then if you're asked to prove that some set is the empty set, a good thing to try is a proof by contrapositive or perhaps a proof by contradiction, because then it gives you something very concrete to work with. Okay, so next time we'll jump into section 5.3, perhaps even start a little bit of 5.4. And after that, there's still a bit more in chapter 5. And also at some point you have a midterm, which I will email you about. All right.